Okay, so today it's going to be a topic at the interface of statistics and algebraic geometry. And everything I'll say is in two papers. First, there was a joint paper with John Hauenstein and Jose Rodriguez. And then we posed some conjecture, and that was subsequently solved by Rodriguez and Dreisma. So the setting is that we have two discrete random variables. The first random variable has m states, and the second random variable has n states. Okay? So then the joint distribution can be written as an m by n matrix with entries pij. So pij represents the probability that the first random variable is in state I and the second random variable is in state j. Now if these things are probabilities, they should be non-negative real numbers that sum to 1. So we're studying m by n matrices with non-negative real entries whose entries sum to 1. I'm going to write m sub r for the manifold of matrices of rank exactly r inside the simplex. So by the simplex, this is the simplex of dimension mn minus 1. That's the set of all such matrices. The set of all distributions is a simplex of this dimension, mn minus 1. And if a matrix has exactly rank r, it lies in mr. And that's a smooth manifold inside the simplex. In particular, M1, those are matrices of rank 1. They will, in our discussion, represent the concept of independence. So independence is a very, very important concept, and that will be matrices of rank 1. And then we will think about MR as mixtures, representing mixtures of R independent distributions. And so these elements, P, those matrices of rank R, they will represent conditionally independent distributions. So you might not, some of the algebraic geometers in the audience might not have thought about these probability statistics concepts in a long time. So let's review this in a very simple, maybe a bit amusing example. So I learned this example from a textbook on introductory undergraduate statistics. So let's ask the following question. Does watching soccer on television cause hair loss? Okay? So every day in the newspaper you read some study, right? I mean, if you eat this food, or you don't eat this food, something will happen. So some kind of behavior or food will cause a certain medical outcome. So here the question is, if you watch soccer on television, do we think that linked to being bald, losing hair? So in this fictional study, 296 British subjects between age 40 and 50 were interviewed about their hair length and how many hours per week they watch soccer, also known as football in England, on television. And we summarize the data in a 3x3 contingency table. So the first random variable is the soccer time. How much do they watch soccer on television? Maybe we group this into less than 2 hours per week, 2 to 6 hours per week, and more than 6 hours per week. So that's our first random variable. That's watching soccer. And then maybe the second random variable, hair length. Maybe by some measure, there are people who have lots of hair, and then a sort of median amount of hair, or very little hair. And then every person, gets an entry. So for example, 28 of the people have responded that they have lots of hair and they watch a medium amount of soccer per television. Okay, so this is exactly the kind of setting we're in. So we have two random variables with m states and n states. In the soccer example, both m and n are 3. Okay, so the question you might want to ask is there a correlation? Based on this data, is there a correlation between watching soccer and hair loss? So in statistics, you would formulate a null hypothesis that these two things are independent. And then in statistics, you never ever accept the hypothesis. You either reject or you don't. Okay. So based on looking at this, what do you think? Well, what I want you to look at is the 2 by 2 minors of this matrix. They're all positive, right? So for example, this times this is bigger than this times that. And they're quite a bit positive. So all the 9 2 by 2 subdeterminants are positive. And this suggests that there is a positive correlation, right? So positive correlation. So this seems to suggest that there's a positive correlation between watching soccer on TV and hair loss. Now, of course, not really, right? Because in this data there is a so-called hidden random variable, and the hidden random variable in this data set is gender, right? So this hidden random variable has 2 states, male and female, and if we knew that, if we knew the data for the males and the females, well then, maybe we knew that 126 of these people were male and 170 are female, and then of course our table U will be a sum of the male table and the female table. Okay. Now the way I've constructed these tables is they're both perfectly rank 1 matrices, right? So this is a rank 1 matrix. It's a perfectly, the male table is perfectly independent, right? It's a rank 1 table. 3 times 12 is 4 times 9 and so on. Likewise, the female table is perfectly independent. So therefore, our table has rank 2. We certainly cannot reject this null hypothesis. So in this example, this was meant to illustrate the concept of conditional independence. So in this data set, this fictional data set, hair length and watching soccer on TV are independent given gender. Is this clear? Okay, very simple example, and it illustrates, the concept of conditional independence and how a low rank structure on the matrix, reveals the hidden variables. So in this case, there was a hidden variable with 2 states, so we broke this table into these 2 tables, and so this is an example of our general discussion if M and N are 3 and R is 2. Is the example clear? This is supposed to be amusing. Okay, so in general, we have some unknown distribution, we have some unknown probability table, and we're sampling from this unknown probability table, and we summarize these data in a matrix like this. So U was a matrix, and so Uij is the number of people that have the first feature in rank I and the second one in rank J, and the entries now are non-negative integers, and the sum I will denote by U++. So the total, that's 296 in the example. That was the sample size. So the total sum of all the entries is the sample size. Now we're going to look at the following question. So we're going to look at the so-called likelihood function of the data. So the likelihood function is simply the monomial represented by U. So the matrix U represents a monomial, and I simply take the monomial, I take the product of Pij, the unknown probability, raised to the power Uij. Okay? Now what is this? Up to a multinomial coefficient that normalizes this, this is the likelihood of observing the table U given that we're fixing the sample size and given that we know the distribution P. Right? So that is exactly the likelihood function. So the likelihood function as a function of the distribution represents the probability that we're going to make this particular observation. So the likelihood, among all possible tables, among all possible, many possible tables, that you could form out of 296 people. This one has a particular probability, namely p11 raised to this power times p12 raised to that power, and so on. And we're interested in maximizing this distribution. Now I should maybe say, traditionally, historically, there are two camps in statistics. There's a frequentist statistics and there's Bayesian statistics. And this is a problem of frequentist statistics. So in frequentist statistics, what we're doing is we're maximizing the likelihood function. In Bayesian statistics, we're doing something else. We're integrating the likelihood function. So in Bayesian statistics, we have some prior belief over our model, and this leads to the mathematical problem of integration. Today, I'm only going to talk about the optimization problem, but they are the two sides of the same coin. So you have some complicated, high degree polynomial function, and integrating this polynomial function is one problem, optimizing this polynomial function is the other problem, and today I'm going to talk about the optimization problem. So I like to maximize this function over all low-rank matrices, over all matrices P, non-negative entries summing to 1 that have rank R. I'm going to write P hat for the optimal matrix, so it's a rank R matrix. I'm going to call that the maximum likelihood estimate for the data U. Okay, so I have some mechanism that has a data table U and produces a P hat that hopefully maximizes this function. Okay, let's talk a little bit about rank 1. That's a very, very simple case. So how do we do this estimation for independence? So this is something we teach our freshmen. We developed a new math freshman class for biology majors, and basically we teach them that in the freshman math class. So maximum likelihood estimate is obtained from the data matrix as follows. You take the vector of row sums and the vector of column sums. You take the outer product and you divide by the square of the sample size. So this is the row vector, so U1 plus, this is the row sum of the data table. So this is the total number of people who watch very little soccer. This is the total number of people who watch a little bit more soccer. This is the total number of people who watch a lot of soccer. This is for the column sums, total number of people with lots of hair, the total number of people with very little hair. Okay? So then I take the product of this column matrix times this column vector times the row vector. That's a rank 1 matrix. But then I want the total entries, this is supposed to be the empirical distribution, so I have to divide by the square of the sample size, and this is P hat. This is the optimal solution. So it turns out for rank 1, this is the unique complex critical point, hence the unique real critical point of the likelihood function on the rank 1 locus, on the Segre variety. And so this is the answer. It's a very, very simple analytic solution. Now if you go outside the math department in KAIST, and you talk to your friends in engineering or applied math or science, they will call this an analytic solution. Now, I am an algebraist, so I'm not doing analysis today. For me, this is an algebraic solution. Okay, so this algebraic, so what other people call an analytic solution, I call an algebraic solution. We're using algebra today. Okay. Now, what does algebra analytic solution mean? It means that P hat is a rational function of the data. Each entry of this matrix is a rational function of the data. So if you take the data U, you evaluate in each coordinate this rational function, you get the optimal solution. Now what does rational function mean? Well, it's a ratio of polynomials, but in particular it's an algebraic function of degree 1. You don't have to extract any square roots to evaluate this function. Okay, so that's rank 1. So this we teach to freshman biologists. Okay? Now let's think about rank 2. So here I formulate the problem. So for rank 2, this is exactly the soccer example. So we have 3 by 3 matrices of rank 2. So the function we want to maximize is the monomial, so the u's are given, the p's are the unknown decision variables. We're interested in rank 2 matrices. So here we have the unique constraint. We have another constraint that says the p's sum to 1. So we have this constraint, that constraint, we want to maximize this function. And then, of course, tacitly we're thinking about the non-negative reals. Now, how do you solve such a problem? So in multivariate calculus, you learn how to solve such a problem, right? You're using the method of Lagrange multipliers. So if you have a constrained optimization problem, using Lagrange multipliers, you can write down the critical equations. So here are the constraints. And in this example, the critical equations say that this 3×4 matrix should have rank at most 2. They should have dependent rows. So what's this matrix? Well, first of all, I flatten out, I vectorize my data matrix. Then the second row, I vectorize my unknown probability table. And in the third and last row, the entries are Pij times the corresponding cofactor. So if the cofactor of the matrix is the derivative of the determinant with respect to Pij, and so each entry in the last row is a cubic polynomial in the p's. So as in terms of equations, so this matrix drops rank if the 3×3 minors, the 3×3 subdeterminants vanish. So if I were to write this in equations, there would be 9 choose 3 polynomials homogeneous of degree 4 in the p's. And this is the system of equations I need to solve. So let's solve it. Well, you type this into Mathematica or Maple or Single or Macaulay 2, and it turns out that there are 10 solutions. Okay? So this has 10 solutions. So if you give me your data matrix U, there will be 10 complex critical points. Among those 10 complex critical points, some will be real. Among these, some will be real and positive, and then among those, you pick the one you like best. Okay? So that's sort of maybe the algebraic approach to solving this problem. Yes, Professor Kork. The question clear? Yeah. So I'm maximizing a monomial over this determinantal variety. And what's the method I'm using? I use the method of Lagrange multipliers, right? I solve a constrained optimization problem. That means I have to look at the tangent space, and the tangent space is perpendicular, so the gradient is supposed to be, the gradient of the objective function is supposed to be perpendicular to the tangent space. That's called Lagrange multipliers. And you learn this in multivariate calculus. Okay? So that's the situation. Let me talk a little bit about, remind you a little bit about our constraint sets. So these are determinantal varieties. So we're interested in the critical points of our likelihood function on MR. So this is the matrices in the simplex of rank R. Now whenever you have an applied problem in algebraic geometry, it's usually formulated over the real numbers, and there are some inequalities. So we're going to make this problem easier in 3 steps. Step 1, we're going to ignore the inequalities. We're going to disregard the inequalities. Step 2, we replace the real numbers by the complex numbers. Now that makes the problem easier. Third step, we're going to replace affine space by projective space. That makes the problem really easy. Okay? So the reason we're passing from the simplex, from probabilities, to complex projective space is to make the problem easier. Of course, after we've gotten some information in the complex projective situation, at the end of the day, we might want to go back, and I will do that at the very end. But we're making the problem easier by passing to the Zariski closure. So VR, the Zariski closure, in projective space, these are the complex matrices of rank at most R. Now what's the dimension? Well, this is the codimension. So the codimension is MR times n minus R. So this is the Mn minus that number is the degrees of freedom that you have in choosing a low rank matrix, right? So if you have a matrix, an m by n matrix, and you want to choose a rank R matrix, well, what you can do is you can pick the first R rows for free, you can pick the first R columns for free, and then those ones are determined. The other entries are determined, so that's the codimension. Now if you have some algebraic variety that walks into the door, some algebraic variety walks into the door, you should ask him or her the following two questions. First question is, what's your dimension? Right? You want to know, is this a curve, is this a surface? How many degrees of freedom do you have? That's the first question. Second question you should ask, what's your degree? Right? Is it a linear space? Does it have degree 1? Or does it have a high degree? Okay? So it's a little exercise, for the graduate students here. Reminder, what is the degree of the determinantal variety? Okay, so as a function, as a formula in M, N, and R, what's the degree? So the degree of a variety is the number of intersection points with the complementary linear space. Okay, so the degree of a curve in 3 space is the number of intersection points with the general linear space. So for example, suppose we look at 4 by 5 matrices. So determinantal matrices here. So then the V1 matrices of rank 1 has dimension 7. Right? So we can first choose the first row, and we have these 8 entries, but we're doing this projectively, so we have 7 degrees of freedom, and the degree of this Segre variety is 35. V2, the matrices of rank at most 2, has dimension 13 and degree 50, and then V3 is given by the vanishing of the 5 2 by 2 minors, a 5 4 by 4 minors, that's codimension 2 and degree 10. Okay, so it's always nice to review the dimension and degree of determinantal varieties, and if you were at Professor Ranestad's lecture 2 hours ago, then of course you know that these are the secant varieties of the Segre variety. So we're looking at the classical Segre variety of projective products of projective spaces and want to study the likelihood function on those varieties. So in this lecture today, I'm only going to talk about the matrix case. I'm going to talk about 2 factors, a product of 2 projective spaces. Of course, in real-world applications, there are many more than 2 random variables. There's not just hair length and, soccer and TV. There's an income, and there are many, many random variables. So in general, there will be many factors in the Segre varieties, and in general, there will be tensors rather than matrices. But today, in my lecture today, in the study I'm reporting on, I will only focus on matrices. 2-dimensional matrices. Okay, so those are determinantal varieties, and we're going to be interested in the algebraic complexity of maximum likelihood estimation. Now the ML degree, by definition, of a statistical model is the number of critical points of the likelihood function for generic data. So if I pick my data table U at random, if there's generally enough, then the number of critical points will be finite. It will be some fixed finite number of complex critical points. I'm going to be interested in this number. Now what do I mean by or a projective variety? Now, statistical models for discrete data, the ones that get used, that get most used, in particular in computational biology, they always either have a polynomial representation or they can be reparametrized to have a polynomial representation. So many widely used models, graphical models, Bayesian networks, hidden Markov models, phylogenetic models, many of the models that people actually use, have a polynomial description, so we can make the problem easier by passing to the Zariski closure in projective space and work on the projective variety. So therefore, it's legitimate in this context to identify statistical models and projective varieties, right? So projective varieties are particular, so statistical models lead to particular classes of projective varieties, such as determinantal varieties. So here's a theorem. So these are the currently known values for the maximum likelihood degree of our rank varieties. So here's the rank in the first row, rank 1, rank 2, rank 3, and so on. And these are some matrix sizes. So for example, for 3 by 3 matrices, well, the rank for rank 1, the ML degree is always 1, right? That was our freshman biology example, right? So for rank 1, we always solve the problem by taking the row sum vector outer product against the column sum vector. So the algebraic degree is 1. Now down here, we also have 1s. For example, if we have a 3 by 3 matrix and want the best rank 3 approximation, well, we don't do anything. We just divide by the sample size, right? So if you have some 3 by 3 data matrix and you want the best, rank 3 approximation, or at most, you just take that same matrix and divide by the sample size. So that's a rational function. That's an algebraic function of degree 1. Now this was the example, this was the soccer example. So in the soccer example, we had algebraic degree 10, 3 by 4 of rank 2, we have 26, and so on. And so until recently, these were the only 2 numbers we were able to compute. And the reason for this is that symbolic computation, to solve these equations in symbolic computation, is quite hard. So if a young person were to enter this field, they might get frustrated very soon using the Macaulay 2. It's not easy. And the reason it's not easy is because you need to clear denominators. Clearing denominators is a very difficult thing to do. That's a saturation problem. So algebraic geometers, they would talk about this. This is really, working with sections of, a sheaf of differential 1 forms. So I'm talking, here about the sheaf of differential 1 forms with logarithmic singularities along the vanishing of the probabilities. And to work with these sections, you have to clear denominators, and that's a very difficult thing to do symbolically. Now we were able to get these larger numbers. We were able to get these larger numbers using numerical computation, which I will explain. Okay? So for example, if you have a 5 by 5 matrix and you're interested in rank 2 model, then the algebraic degree, the ML degree is 6,776. So this is the expected number of complex critical points. And again, among these critical points, there will be some real, there will be some, positive, and this includes all the local maxima, all the local minima, and all the saddle points. So from a practical point of view, these numbers give you a hard upper bound on the number of modes, the number of local maxima of the likelihood function, and they give you a sense of the algebraic complexity of solving this problem to optimality. Okay? Now one more remark. There's a beautiful work, a recent work of Junhe, who spoke here last week, who identifies the ML degree with a certain topological invariant of this is the very affine variety. So I take my determinantal variety, this is my divisor D, so I remove mn plus 1 hyperplanes. That's a very affine variety. That's a subvariety of a torus. That's an open variety with a distinguished boundary. It's a pair, as they would say in algebraic geometry. And I'm interested in this sheaf on this open variety. Now, if this variety were smooth, this would be just the topological Euler characteristic. Okay? So this is quite nice, right? Because even if you don't care at all about statistics and likelihood, but maybe you care about, the Euler characteristic of low-rank matrices, then this gives you a lot of information. Now, it's unfortunately not quite the Euler characteristic because of the singularities. What it is the so-called, it has to do with the so-called CSM class, the Chern-Schwarz-McPherson class of the characteristic function on this constructible set, but it's essentially, morally, it's the Euler characteristic. Okay? So these are the known values for the ML degrees. Now if you look at this table, what's the first thing you notice? Dan, anything you notice in this table? They're palindromes, right? You go down the column. This is amazing, right? So you go down the column and they're palindromes. For example, here, this 843, so for 4x5 matrices, of rank 2, it's the same ML degree as this one. And for us, this was a big surprise when we first did this last fall, because we only knew these numbers and we didn't go this far. So this was a very big surprise. So I'd like to explain to you what's going on. This was a big surprise for us. So there seems to be a certain duality going on, and I'll talk about this. Okay, so just again to clarify, right? So here, 4x5 matrices have dimension 13, they have degree 50, and ML degree 843. Okay? Let's talk a little bit about formulation, how you set up the solving of these equations. So the geometric formulation, so if you want to actually solve this in some mathematical software problem, a system, so P is a regular point if and only on the variety VR, if and only if the rank is exactly R. And at such a point, we have the tangent space, and its dimension is equal to the dimension of the variety. So Rn plus Rm minus 2, it's our dimension. Rm plus Rn minus R squared. So we have the orthogonal complement. Its dimension is the codimension of the variety. Now the other thing we do, the log, we form the log likelihood function. See, whenever you have a product of things, a complicated product, if you want to take the derivative, it's a good idea to take the logarithmic derivative. So we're going to look at the log likelihood function, LU, and we lift this to a function on projective space. So log LU, when you write this on projective space, so it's the sum Uij times log Pij, and then you take the derivative of this. Oh, let me do this again, I'm sorry. LU, again, is the product of Pij, Uij, but down here you put the sum of Pij to the sum Uij, the sample size. So this is now a rational function, homogeneous of degree 0, right? So we're extending this to projective space. Then the logarithmic derivative of this with respect to an unknown Pij is Uij times divided by Pij minus U++ divided by P++. So these are just the partial derivatives. So this is an honest function, rational function on projective space, and these are the partial derivatives. Here's the proposition. So a regular point, a matrix of rank R, is a critical point for this rational function if and only if the linear space perpendicular to the tangent space contains the gradient. Okay, so this is exactly what I said. That's called Lagrange multiplier. So Lagrange multiplier says the gradient of our function should be perpendicular to the tangent space at the point of interest. So this is this is a system of equations we need to solve. Now if you take this system, this is a geometric description, but now you need to translate this into equations that you need to solve. And that's where it gets a little bit ugly, and there are many formulations, and I just want to give you on the next slide the formulation that actually works. Okay? And that's sometimes, when you do numerical analysis, then it's not so beautiful. So this is a bit ugly. So this is the linear algebra reformulation. So let m be less or equal to n. What we're going to do is we're going to rewrite the low rank constraints in a parametric form. So we're going to set up matrices of unknowns P1, R1, L1, and lambda of these various formats. So this, respects, I set up an unknown for each block. So according to this block decomposition, I set up matrices. These are identity matrices. So here's a left matrix L, there's a right matrix R, and then my matrix P I set up to have this factorization, which forces it to have low rank. So then here's the formulation. So if you have a general m by n data matrix, we form this red system of polynomial equations. So this is the matrix product R lambda L transpose. This is the Hadamard product. So the star is the core entry-wise or Hadamard product of two matrices. So if you have two matrices of the same size, you can multiply them entry-wise, the Hadamard product. And then this red stuff is mn equations and mn unknowns that has finitely many complex solutions, and the corresponding matrices P are precisely the critical points of the likelihood function on the determinantal variety. So this is a bit ugly, you don't have to understand that, but that's sort of the formulation that actually works the best when you solve this. Right? I'm just saying this is the correct way of saying Lagrange multipliers. Symmetric matrices are important. Here's the same table for symmetric matrices. So here is you have two random variables, but they're identically distributed. Okay, so this comes up a lot, in genetics. You have the two sides, from your mother and your father. So for n equals 2, this is called the Hardy-Weinberg curve, and it's important that you have a 2 along the main diagonal. Okay? So this is the model for symmetric matrices. So this is independence and mixtures of conditional independence for two identically distributed discrete random variables. So here are the known ML degrees for rank R symmetric matrices. Again, 3 by 3 matrices of rank 2. Now it's 6. But again, we have this kind of symmetry down here. These one we were not able to do. So for example, 5 by 5 matrices of rank 3, it's 1394. Okay, so before I get to explaining the duality, I like to show you a numerical example for this entry 6. So I'd like you to think a little bit about this entry 6. So here's an instance. Here's an instance of this. Okay, so let's look at symmetric 3 by 3 matrices, and suppose I have the following data. Okay, so U11 is 10, U12 is 9, and so on up to U33 is 7. So I chose those data. Okay? So I want to find the best, in the likelihood sense, rank 2 symmetric matrix that explains this data. Well, so I set up my formulations, I solved the problem. It turns out there's 6 complex critical points. They're all real and they're all positive. Okay? So in this case, all 6 critical points are real and positive. They're all in the 5-dimensional simplex. And here they are. Okay? So here are the coordinates. So this is the first point. So P11, da 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 da. So here I have 6 real numbers that sum to 1. Here I have the log likelihood value for these numbers. Okay? So this is the logarithm of a real number between 0 and 1. That's a negative number. You with me? Yeah? The logarithm of a number between 0 and 1 is negative. And a negative number is largest if the absolute value is smallest. Okay? So this is the largest value. This is the winner. Okay? So this is the global solution. This point is in the simplex. This is a rank 2 matrix, and this is the optimal solution. These other 2 points are local maxima. So I have 3 local maxima, one of which is the global maximum. I have 3 local minima, and this is the worst point, okay, down here among the critical points. 3 local maxima, 3 local minima, for a total of ML degree 6 solutions. Now, can you write these coordinates in radicals? Okay, that's a crazy question, right? That's a crazy question that only an algebraist would ask, right? For a numerical person, this is the answer, right? But I want to ask the question, can I take these numbers? These are some floating point numbers, right? 0 point, this goes on, 1, 6, you know. Can I actually write these exactly in radicals? Well, maybe not, right? Because these points define an extension of degree 6, right? So if you take my system of equations, you type it into computer algebra system, you solve, eliminate all but one of the unknowns, you get one equation in one variable of degree 6. And you know from undergraduate studies that equations of degree 6 you cannot solve in radicals. Okay? So maybe you cannot solve this in radicals. Well, it turns out that you can. Okay? It turns out that the Galois group for this problem is not S6, is not the symmetric group on 6 letters. It's in fact a subgroup. It's a symmetric group on 4 letters. Okay? This has a smaller Galois group. It's a solvable group. So I picked this example because S4, the symmetric group on 4 letters, is a solvable group, so I can solve the equation. So let's solve it, okay, just for fun. So if I take my data set, I write down the critical equations, I eliminate all but one of the unknowns, I get one polynomial of degree 6 in the lower right entry of the matrix, P33. Okay, that's a polynomial. And then you solve it, okay? So, you know, so P33, the solutions are like this. So this is, you know, zeta is a primitive third root of unity, so, and then omega 1 is the square root of this rational number, and then omega 2 is the cube root of this number, and then omega 3 is the square root of that number. Okay? So this is the exact representation of P33. Okay? So some people prefer this way of writing the number. Some people think that this is easier, a better description. I think that this is easier. But of course, you know, beauty and all that is in the eye of the beholder. Okay, it's the same number question.
They give real numbers?
Pardon me?
They all give real.
They happen to be real numbers, that's correct. They're all real, yes. I mean, that's when you run Cardano's formula, right? So when you solve cubics and quartics, very often you have to throw in roots of unity, complex numbers, but at the end you get all real numbers. Okay? So it's a little extra, so you can try this, right? So try, you know. Right, so if you solve this equation, then in radicals, in the formula, you will see complex numbers, but of course the roots are all real. Okay, now why am I showing this? Well, the reason I'm showing this, I wanted to illustrate why is it that the Galois group is smaller here. Why is that? Well, the answer comes from the table, right? There seems to be an involution on the columns. Well, and there seems to be a bijection between this 37 and that 37. There seems to be a bijection. Well, if there's a bijection, then there's an involution on this set. And there's an involution on that set. Now, if you have an enumerative problem that has extra structure, then the Galois group drops. And the size of the Galois group drops. That's why, for example, the Galois group of the 27 lines on the cubic surface, a topic we'll return to on Wednesday, is much, much smaller, right? The Galois group of the 27 lines is not the symmetric group on 27 letters. It's much, much smaller. It's a tiny group. It's the Weyl group of V6, to be discussed on Wednesday, right? So if you have an enumerative problem that has symmetry, that means the Galois group drops, okay? And so here, that's what happens. That's why I showed this example. Okay, so let's explain the duality. So two theorems. So this was proved. In the first paper, this was a conjecture, and then Dreisma and Rodriguez proved it. So the first version is just a simple numerical version. So suppose M is less or equal to N, and consider either general or symmetric matrix. It works for skew-symmetric matrices too. So then the ML degree for rank R equals the ML degree for rank M minus R plus 1. Okay? This says if I look for rank R or co-rank R minus 1, it's the same. the degree will be the same. So that's exactly the symmetry we saw in the colors. Now let's sharpen this. Let's make this a little bit more precise. Okay? So suppose we have a strictly positive data matrix. Let's assume we have a strictly positive data matrix. Let me write omega u. Think about this as a dualizing matrix. So this dualizing matrix is also an m by n matrix, and in the entries in row I and column j is this expression. So uij times ui plus times u plus j divided by the cube of the sample size. Okay? Then we have the following theorem. If we look at the complex critical points of the likelihood function on rank R, on the rank R variety, I can label them. I can write them as P1, P2 up to PS. I can order them in a particular way. The S critical points, I can order them. And similarly, I can look at the critical points of the same function on the co-rank R minus 1 variety, and I can label them as Q1, Q2 up to QS, same S, such that the following bijection holds. The Hadamard product, the entry-wise product of P1 times Q1 is equal to the Hadamard product of P2 times Q2 and so on, and they're all equal to omega u. Okay, that's the statement. Okay? So I can pair them up so that the Hadamard product becomes equal. Now if you paid attention, or if you're used to these kind of statistical things, this is a trivial statement if R is 1. Let's look at this for R equals 1, right? If R equals 1, well, here we're looking at, independence model, that's rank 1. And then this is no constraints, right? Well, that's exactly, this is exactly this times this over that squared. That's exactly the freshman biologist solution in rank 1. That one divided by the sample size is the trivial solution for the maximal rank. So this is obviously the right statement for the independence model. But what we're saying is this is also true for other in-between models. Now in particular, this bijection preserves reality, positivity, rationality, arithmetic structure, right? Because I can Hadamard divide, right? This matrix is given. If I know QS, I can recover PS. I just divide in every entry. So if this matrix has rational entries, that matrix has rational entries. If that matrix has positive real entries, that matrix has positive real entries. So the number of positive real solutions is preserved. Moreover, maxima become minima, right? So the problem of maximum likelihood estimation in rank R is the same as the problem of minimum likelihood estimation in co-rank R minus 1. Now that immediately has some nice implications, right? Suppose one of the problems is easier to solve than the other. Well, I can just solve the other problem. So, So for example, in this kind of table, it's typically the case that the low rank numbers are easier to compute. So it's easier to compute this many critical points here than it is to compute this many critical points here. Well, if I want to solve the maximum likelihood problem here, I compute the critical points there. I find the minimum, the worst point there. It gives me the best point down there. Okay? That's what this formula is. Okay, so that's the duality. Now this duality, as I said, was proved in the second paper, but it's also interesting to us how we got to this duality. So by getting to this statement, we did thousands and thousands and thousands of numerical computations. And I like to tell you how this was done. Okay, so I'd like to tell you a little bit, why we're able to get these numbers. So nowadays, there's suddenly a lot of interest in numerical algebraic geometry. And we used numerical algebraic geometry, in particular the software Bertini, to test thousands of examples before formulating the conjecture. Now, if you're used to computing in algebraic geometry, in the last 20 years, symbolic methods have become pervasive. People compute, syzygies. People use software like Macaulay 2 to do lots and lots of experiments in parts of algebraic geometry. It's a pretty standard technique by now. These symbolic methods are Grobner-based. The engine that drives these kind of machines are symbolic calculations in exact arithmetic that use Grobner bases. Okay? Here, this is a different paradigm. So Grobner bases get replaced by something called homotopy continuation. These are purely numerical methods, and it's exactly the kind of numerical homotopy continuation that we discussed when we talked about the central curve on Friday. You have some implicitly described curve, and you numerically track the curve, okay, by a steps, predictor, and corrector methods. Okay? So this can be used to find all complex solutions of systems of polynomial equations, but you can do much more with this. You can compute irreducible decomposition, you can compute Chern classes. This is pretty sophisticated. Many of the things that you can do in Macaulay, you can now do in Bertini. So if you're interested in Hilbert series, so many of the algebraic invariants you can also get in Bertini now. So these are the developers: Bates, Hauenstein, Somesi, and Wampler. And I think very soon, I think in the summer, there's a new textbook that comes out where they describe Bertini and the mathematics behind Bertini. And anyways, this is a little, we have a new computer science institute in Berkeley, and this numerical methods will also be one of the topics that will be featured next fall. Now, why did it work so well in this case? So I like to argue that for problems like this one, for maximum likelihood estimation, numerical software has big advantages for symbolic software. And here's why. Okay? Suppose you're interested in some model, maybe 5 by 5 matrices of rank 3. That's some meaningful story having to do with soccer and hair and income and so on. Okay? So you have some particular model you're interested in. You pre-process that model by solving the likelihood problem once. You pick a data matrix U, 0, and you run this for a long time, and you find all the critical points up to some high accuracy once. Okay? Now, since you pick the data U0, well, you can pick it in a way that you want. It could have complex entries. It could be very well conditioned. You pick a matrix that has very good numerical conditioning. Okay? And you run this for a long time, and when you're done, you've solved this model once. You save all the critical points on a file up to many digits of certified accuracy. Okay? So now I claim the subsequent computations for any particular data U will be very fast, right? Because now you give me your favorite data matrix U. Okay? So then I start at my 3,000 critical points for U0. I numerically track them in data space, right? From U0 to U0, and this is utterly parallelizable, right? Because if the ML degree is 3,000, I can give each path to a different processor, right? If I have whatever the ML degree is, if I have that many processors, I can independently track the path, and it's very fast. Okay? So here the homotopy amounts to changing the data. I should maybe say again, this takes place in complex space, right? So I will never run into discriminants, right? So if I trace, maybe I should explain this. So here's my data space. Okay. So here for U0, I have, all these solutions. I want to find them. But if I do this over the real numbers, they might cross over. I might have bifurcations. I have all kinds of problems like this. So typical picture over the real numbers looks like this. And this would be bad, and this would be bad. But this never happens, right? Because down here, I replace this. I do this over the complex numbers. And by choosing my path in the complex plane, I'm going to avoid, these finitely many points, right? I can walk around this in the complex plane, right? a hypersurface, the complement of a hypersurface is connected. Okay, so no problem. Okay, so that's how Bertini works. Now here are some examples, time needed to preprocess and then solve subsequent instances on this kind of framework. So for example, here for 5 by 5 matrices of rank 4, so it took a very long time, 150,000 seconds to do the first instance by some other methodology, but every subsequent instance takes only a minute or 2 minutes at most. Okay? So that's why it's a good idea for problems of this kind to, of course, we experiment with Macaulay, but then if you want to have real answers, you need numerical methods. Okay, so I have only 2 or 3 more slides to go. I'm almost done. So I'll be under time again. Sorry. Now I cheated a little bit. Okay? So I need to tell you, did we solve the problem? No, we didn't solve the problem. First of all, we only solved small problems. Also, we worked on the wrong problem. Okay? From a statistical point of view, we asked the wrong question. Now why? Well, statisticians and applied people, they don't care so much about the rank of a non-negative matrix. What they care about is the non-negative rank of a matrix. Okay? So really, let me phrase this, they're not so much interested in our model MR, but they're interested in the so-called mixture model. So the mixture model is the set of all m by n matrices, A, lambda, B, where A is non-negative with rows summing to 1, lambda is diagonal with entries summing to 1, all non-negative, and B is columns summing to 1. That's a low-rank factorization, but the factorization should be non-negative. Okay? So why is that important? Why is that important? Let's go back to the soccer example. Okay? Here we had a rank 2 matrix. Okay? And I decomposed this matrix into a sum of 2 rank 1 matrices. What I want is that these entries are non-negative. Right? So I'm interested in, whenever I decompose a non-negative matrix and it's a low-rank decomposition, I want the sum ends to be non-negative. And that poses a hard constraint. So that's the so-called mixture model. Okay? So the mixture model is really the set of, so what we're really interested in are the matrices in the simplex of non-negative rank at most R. Right? So these are matrices that I can factor, right? A low-rank matrix that I can factor as a non-negative matrix with R rows times a non-negative matrix with R columns. Okay? Now here's a little proposition. So if R is 2, then they're the same. So if you have a big matrix of rank 2, a non-negative matrix of rank 2, its non-negative rank is also 2. But in general, that's false. In general, the mixture model is strictly contained in the low-rank model. Okay, so the mixture model is strictly contained. Let me give you a concrete example. Or just to take this 4 by 4 matrix, 1, 1, 0, 0, 0, 1, 1, 0, cyclically 0, 0, 1, 1, 1, 0, 0, 1. Okay, let's make it a distribution. So 1/8. So there's an example. This matrix has rank 3, classical rank 3, but non-negative rank 4. Okay, so it's classical rank 3, but if you try to factor it as a 4 by 3 times a 3 by 4 matrix, you have to use negative entries. So I have non-negative rank 4. Now, what people in applied contexts really want, they want to maximize the likelihood function not over the low rank model, but over the mixture model. Okay? So that makes the problem much, much more interesting and harder, and we really haven't addressed this quite yet. The other thing that statisticians do, they really work in the parameter space of the parametrization. Right? So this parametrization, what does it say? It says we have a parameter space, a product of convex polytopes. So A gives us a point in this polytope. Lambda gives us a point in this simplex. B gives us a point in that simplex. So we have a map, an algebraic map from this product of simplices into a large simplex, and we're interested in the image. The image, of course, by Tarski's theorem, is a semi-algebraic set, but this is a very difficult semi-algebraic set. So the way statisticians operate, they don't even try to find the global optimum. They're using local methods, and one that's particularly widely used is the so-called EM algorithm. There's something called the expectation maximization algorithm. That algorithm does local improvement steps in the parameter space, and hoping to find a maximum. That maximum will be typically on the boundary here, and so we're currently working on looking at the boundaries, trying to assess the ML degree of the different strata in the boundary, so to tie in the algebraic discussion I presented here with what's actually done. People actually do is use the EM algorithm. Okay, so time is up. Let me end by going over a brief list of references to sort of give you the context where there are various places. So first, here's the book by the Bertini team, Numerically Solving Systems with Bertini, coming out very soon. There's a paper by Feinberg and co-authors. So in statistics, these things are called latent class models for contingency tables. And this is a very nice discussion of exactly what I talked about in the language of statistics of this problem. This is a nice one, Hauenstein and Sottile. So oftentimes, algebraic people get very worried when they hear about these numerical methods, because it can fail. It could happen that we, lose some paths. We might miss some solutions. And there's a very nice thing called the alpha theory that was proposed 20 years ago by Steve Smale. So Smale was very interested in numerical methods for solving equations. And he proposed a theory, the alpha theory, for doing path continuation in a certified way. So take very small step size and provably stay on the path. Okay? And this was now implemented for the first time by Hauenstein and Sottile. And in some of our calculations, we also use the alpha certified way. That slowed down the calculation by a factor of about 100. But then you get a proof that, it's actually a proof. This is the paper by Jun He, very beautiful paper on the maximum likelihood degree to appear in Compositio. This was the very first paper solving the likelihood equations where we got the first numbers and where this problem was proposed. Same discussion in the computational biology context in the book with Pachter. And finally, the last one. So I've been always obsessed for a long time with the case of 4x4 matrices. And there was one particular data set I was interested in. And 4x4 matrices are particularly important, right? Because the rows are called A, C, G, and T, and the columns are called A, C, G, and T. So if you have matrices or tensors of 4x4x4x4, that's particularly interesting in molecular biology. So we had a particular, table U that we were interested in, and I wanted to really find the optimum for this table. And this table came out of this book. And I ran the EM algorithm, right, 100,000 times, and there were maybe 12 local optima. Okay, so, and one of them seemed to be the best. But I wanted a proof that this was actually the global optimum. So I gave some lectures at ETH Zurich in Switzerland, and to challenge the students, I offered 100 Swiss francs for somebody to prove that one of them was actually the optimum. Nobody solved in Switzerland, but then a couple years later, especially Ming-Feng Zhu in North Carolina solved this problem, and so they published this in Math of Computer Science. At that time when they wrote the paper, they didn't know, but of course now we know, we know the truth. Now we know there are 191, critical points. So at that time we didn't have the table. Now we have the table. So now we know, of course, that, oops, here it is. That was this case. So this was the 100 Swiss francs problem. Okay, thanks for your attention.